So welcome everyone. My name is Erin Cook. I am part of the Inner Orbit team. My background is in upper elementary education, special ed, and coaching. That was my first passion, my first love, but now I'm in the NGSS and supporting educators all across the country and the world, which is super exciting. My main role with Inner Orbit is supporting everyone's journey throughout the NGSS and creating sessions like we're in today. And my favorite thing about being a science educator with teaching upper elementary is maybe the first time really diving into really cool science topics. Not that K3 doesn't have any love, but it might have been their first time really experiencing that. So it was just an honor being at the start of kiddos' journey in science. And then I was at a K-12 school, so I could also see how students progress through middle school and high school in their science journeys as well. So that's my favorite thing about being a science educator. And this is my colleague, Brendan.
Howdy, y'all. My name is Brendan Finch. You can tweet at me at BirdBrainFinch if you're into that kind of thing. I taught middle and high school science for 7 years in Los Angeles, and I've written most of the articles and content on both our leveled reading website, Rocket Lit, and also Inner Orbit. And what we're going to talk about today is kind of a crystallization of our work with districts and our work in writing these assessments, seeing how students respond to them, and then iterating upon those things. My favorite thing about being a science educator, facilitating students' ability to question the world around them. And this is like one of those things where you're kind of happy you did it, but it's kind of a pain in the butt. The reason we are even able to be able to talk to you about this is that we've written a ton of assessments and we've worked so hard to find phenomena and write questions that scaffold up to the level of rigor expected of students. If you're a 3-5 or a middle school or a high school teacher, or even if you're a lower elementary teacher, what the NGSS asks of students and what other three-dimensional standards ask of them is really, really complex. So we work very, very, very hard to make this more accessible and make sure there's a ton of data that comes in on that. So if you're interested in checking out our website, Erin's going to drop a link in the chat, so you can find a time on our calendar. We're not really going to talk about Inner Orbit today at all. Maybe we'll touch on it a couple times, but we have these awesome reports and data because the NGSS are so complex. We break down every element of a DCI or an SEP or a cross-cutting concept that's covered in grade levels 3-5 and in 6-8 and in 9-12. And then we aggregate all that data and we chop it up by performance expectation. And we're just trying to be as specific and clear as possible to make sure that y'all have great data and you can track student progress on these complex standards.
So our objective and our 60 minutes time together today is to be able to analyze assessment items covering the SEP, developing and using models for complexity and detail. Those are two really big words that we're going to hit on a lot today, but we're going to be able to evaluate assessment items. So items maybe that you already have in your practice, or if you're familiar with Inner Orbit, you can look at our assessment items as well, and be able to see the level and complexity and detail of our questioning around this SEP, and then decide when to use what kind of questions in your instruction. And without further ado, let's jump into our first activity, which is a throwback to the childhood classic, Connect the Dots. And we'll probably have a little bit more positive energy than our friend here in the GIF. But the purpose of this activity, as I mentioned before, is to deeply dive into the science and engineering practice of developing and using models so then we can better assess it. Before we jump into the activity, Brendan is going to give us some background knowledge so we're all on the same page.
So we realize that some of y'all are just beginning your journey towards the NGSS. We want to make sure we define these terms before we dive in super duper deep. So first off, what are the 3 dimensions of the NGSS? If you're familiar with this, then that's awesome. But this is for y'all that need a little bit of support because you're just getting started. So today we're talking about SEPs. These are the science and engineering practices. This is what students do. These are skills that students will demonstrate proficiency on and can use to make sense of the world and apply to novel phenomena. So typically this is things like developing using models, constructing explanations, planning and carrying out investigations. These are skills that sort of transcend science and they're critical thinking, usually synthesis, analysis, all that good stuff. The second dimension of the NGSS are the DCIs. These are sometimes called the disciplinary core ideas. And this is what students know. Y'all have been teaching this for a long time. This is the content. This is the mitochondria is the blank of the cell. You're super familiar with this. This is easy. In the future, we actually will be doing sessions on DCIs and the K-12 progressions of DCIs. So stay tuned. If you're into this and you want to dive deeper into, I think chemical reactions will be the first one, and we have a few more planned as well. The third dimension of the NGSS is cross-cutting concepts. And these are how students think. And I like to think of them as thematic elements. So like in literature, there are these thematic elements that crop up again and again and again, kind of like these archetypes or these ideas, these formats. So patterns and scale and structure and function are kind of like these thematic elements that we see throughout the NGSS and throughout Earth, life, physical science. And the reason that we want to define these and the reason these are important and so beautiful, and this is like the beauty of the NGSS is, so each of these are kind of like different tools in students' toolbox. So they have their knowledge, they have these skills, they have this understanding of these thematic elements, the cross-cutting concepts. And what we're looking for students to do is then apply those to a phenomena or a problem. So look at something they've never seen before. This is what scientists and engineers do all the time professionally, and they make sense of it by applying those things to something new. It's imperfect and it's really hard. And so we need to scaffold up to that. Today, we're just talking about modeling, and I'm excited to kind of break that down for you and talk a little bit about what modeling is exactly. So modeling is usually it could be a diagram, a physical replica. They could be mathematical. Math is science too. They could be analogies and simulations. And commonly, we see this as representing or generating or communicating ideas. So students will build a model to describe the way something is working. What's really important about modeling, and I think this is the most important bullet on this slide, is that they bring certain features into focus while obscuring others. So if we're looking at the process of like mitosis or meiosis, these are complex fluid processes that are literally occurring, there's no like stage 1, stage 2, stage 3. We have like put these things in there. So what we're doing is we're obfuscating some of what's happening in the actual process and, to clearly communicate and describe what's going on. Models are really helpful because they can provide evidence for something. So if I'm trying to communicate an idea to you, here is the evidence. So these are the stages, these are the steps, this is the process, what happened before and after. And then I purposefully put limitations on my model. For engineers, models provide them with an opportunity to evaluate and refine. So they're able to test solutions, they're able to build replicas of something at a smaller scale to then show how it might work at a larger scale. Cool. The two things I want to define also to make sure you know what they are. So they're the grade bands and the elements. So grade bands run along the very top of the standards right here. In K2, 3, 5, 6, 8, and 9, 12, they've grouped together each of these different things that they're looking for students to do. As students progress through the grade levels, things become more and more complex, more and more rigorous. So we're going to use the term grade bands to refer to K2, 3, 5, 6, 8, 9, 12. And the way the standards are broken up, within middle school, within late elementary school, within high school, students have elements that they're expected to demonstrate proficiency on. And those are the bullet points in there. So each of these bullet points are elements within a grade band. In grades K2, there are 4 elements that students need to demonstrate proficiency on, perform in order to show that they've achieved what we're looking for them to achieve. In 3, 5, they become more complex, 6, 8 more complex, 9, 12 more complex.
So to begin, you're going to select one of the 4 elements in K2. Then you're going to look through the 3, 5 band to see which element is the next step from your selected K2 element. And you'll continue that process for 6, 8, and then 9, 12, connecting the dots between all of the grade levels and the elements to see how they unfold. So once you have your Jamboard open, I recommend using the pen tool over here on the left. You can change the thickness and the color of your pen tool, but then go ahead and circle the element that you chose on the previous page. And then, as I mentioned before, you're going to read through the rest of the grade bands and connect the dots between the elements of how you think they unfold from K2 to 912 of what's the next stepping stone for students. But what I'd love for you to do now is to kind of summarize what you experienced as you were looking through those elements across the grade bands. So we're going to do that by answering this question in the Zoom chat. So in one sentence, describe how the element you selected in K2 developed over time. What did you notice as you were connecting that foundational K2 element to the other elements across the higher grade bands? So I do want to show you how NSTA groups these elements over time and how they unfold. They group them by 3 kind of threads, and you're going to notice that they group some of the elements together in these threads. But they are exactly what you guys are saying, is that these elements progress over time, become more detailed and specific. Themes like mathematics or vision or comparing multiple models, you'll see that increasing in the higher grades. So really the main purpose of doing this activity and seeing how the elements are progressing is to not only help design a curricula with more intentionality, but also add specificity and more intentionality into our assessments. That we're not just assessing modeling, whatever that vague thing might mean, but being able to know the specific elements and what our expectations are per grade level in our assessments. So thank you guys so much for engaging and being active in that activity. That was beautiful. So speaking of assessments, we're now going to move into our second activity where we're going to hear from Brendan in a mini presentation. He's going to build off what we just did about talking about the progressions and the elements and talk about how we can add that in our assessments, assessing this SEP of developing and using models. He's first going to talk about some considerations to keep in mind when assessing any SEP, and then we're going to dive into some really specific examples of what it looks like to assess this bad boy. Well, without further ado, take it away, Brendan.
That was fantastic. Okay, so first we're going to talk about a really basic consideration, and that is representation versus sense making in SEPs. This is really, really crucial because the majority of the assessments that we see teachers either creating on our site or sending us are representation questions. And if they, I think it's because folks usually don't know the difference between these two things. So I want to make it really, really clear for you. So representation is all about communicating ideas that students have previously learned. A good example of this is draw a model to show how molecules of water change from liquid to gas as water boils in the stove. So students have seen this before. They've talked about phase change. If we're giving an assessment on phase change and how particle motion changes, having them draw another model of phase change, water boiling, is a representation. What they're doing is they are representing knowledge. They are not making sense of the world around them. Now, that doesn't mean that this isn't important. It's very important for scaffolding. There's no way your students are going to be able to make a model to explain how something, is changing phase, and thus we see this phenomenon that explains what's going on, unless they've done that prior. So really important for scaffolding. You should have students draw models of representations. I think that's a very basic thing. So we talked about a phenomenon in class. Now I want you to draw a model to represent that phenomena. And then later on, when we assess it, we're going to have something new that you've never seen before, and you're going to have to make sense of it. And so though that's awesome for scaffolding and for formative assessment, it is insufficient evidence of SEP proficiency. If students are drawing a picture of something that they have seen before, then you cannot say that they are proficient in that SEP. They need to be making sense of something, and that's where sense making comes in. So this is what we work very, very hard on, and this is about explaining why or how to make sense of a novel phenomena. So at the most important thing is the why or how, and secondarily, and I mean, it's obviously connected, is that it needs to be a novel phenomena. So if they've seen this thing before that they're looking at, this is not, it's not sufficient evidence of proficiency on the SEP. In order to develop a model, it has to be looking at something new, connecting previous ideas. So if we've talked about what happens during phase change when water, goes from liquid to a gas, then we're looking for students to use those ideas and all those skills in developing those models or representations, and then applying them to make sense of something new. So let's talk about scaffolding, because this is one of the big things that we're here. These skills build in rigor and complexity, and it gets intense. You saw this like mathematical and computational models at the high school. The higher grade levels are totally inaccessible without mastering lower grade levels. If students can't represent a concrete event, they're going to have trouble doing something abstract. And they're going to have a lot of trouble looking at multiple models or limitations of different models, moving between types of models. The formatives are a great place to do this, and we are going to give you some concrete examples of how to use formative assessment to scaffold up these assessments. You can ensure that students can access prior grade level bands, which is why we had you do that activity. If you're a 3-5 or a 6-8 or a 9-12 teacher, knowing what students should be coming to your classroom, with is really crucial, because then you know where you need to bring them to and then where they need to go after you. I would consider representation questions, I think, as often as possible. I'm going to give you, I think we have like 9 different examples of sense making for all these questions. You're going to have so many, you're going to be like, not want to talk about phenomena for the rest of the day, maybe the week after this, because we're going to throw some phenomena at you like it's our job, because anyway, so I would consider representation questions, and I'd also give students examples of flawed sense making. So as often as possible, I'd say, here's a model, here's a CER statement, here's an investigation plan. There's something wrong here. What's wrong? And then even some multiple choice questions to explain what's going wrong and ask students to tease it apart. When students have to generate something on their own with no scaffolding, that is tough stuff. So as much as you can give them to scaffold up to that, give them opportunities to see examples, collaboratively build a model before you build it on your own. These are great, great, great instances where you can scaffold up to the level of rigor that's expected of your students. 2 things, well, 3 things, but on this slide, 2 things we're going to talk about: how to use the SEPs for NGSS assessments. And you, all of y'all here are going to have to do this on your own in a couple minutes with that little annotation tool. So pay attention to this, because this will be used later. Complexity. The first thing is that these build in complexity. Those grade level bands become more complex. You just saw this, and a bunch of the analyses said they become more complex over time. That's important. And then the second thing is that there are specific details that are in the elements at each level of complexity. So at 3.5, students just identify limitations. And then at 6.8, they evaluate limitations. They develop a model to show what happens if a variable is changed. And at 9.12, they need to develop models to show like interactions between 2 systems. It gets much more complex, but each of those details are elements that are important, because if you just have students draw models to explain a process, you're actually only hitting a very, very small number of elements within each grade level band. So we're showing you this, and we're going over this task. We're going through these tasks to make sure that you understand when you're developing using models, there are many different tasks you can give students, and they should be demonstrating proficiency on each of these throughout 3.5, 6.8, 9.12. And data is really important too. And guess what? That's what we do. We spend so much time, literally all day, every day, thinking about how we can give you data on the NGSS that would be helpful to scaffold up from students from 3.5 to 6.8 to 9.12. Aaron's going to drop a link to our calendar in the chat, and we would absolutely love to support you with a pilot of Inner Orbit. We can do PDs like this with your teachers or with your colleagues. If you are a teacher, we would love to help out. We think about this a lot, and things have changed in the last couple of years, and our new assessments reflect what's changed in the past. So we're constantly developing, and we'd love to have your feedback and also to just support y'all. First thing we're going to do is talk about complexity. We're going to look at it across grade bands. We're going to give you all those examples. Emily, again, you're going to have more phenomena than you ever wanted to see, and lots of examples of analyzing this for complexity and sense making, representation, etc. The first one is, why does cutting onions make you cry? For some reason, when you cut these onions, the solid object, it makes you cry. So we have a phenomena. There's a whole description of what's going on on the website, but we're not going to go over that. The question is, pictures A and B are meant to represent different types of particles. Which statement would best describe a relationship between pictures A and B? And we have the answer here. So picture A might represent the onion, and picture B represents the particles as they move through the air. So we are looking at levels of complexity. How much rigor and how much complexity is being evaluated here? Really important. The content is different than the level of complexity of the SEP. So you may be a teacher, and maybe you've even used this phenomena from our website, but just because you're familiar with the content does not mean that that's relevant. So let's go through this. In K2, students are representing concrete events, things like day and night, things that are very concrete, observable, tangible. In grades 3-5, they go to building and revising models. And these can represent events or design solutions. It gets a little bit more, like complex. We have, movements of things like the sun and sun, moon, earth system, looking at how, spheres between the biosphere and the atmosphere and the hydrosphere all interact. It gets much more complex at grades 3-5. And then at 6-8, they're now developing, using, revising models to describe, test, and predict more abstract phenomena. Key term is abstract phenomena. So for this thing that we're looking at here, this is a grade level 3-5 of this. They're representing an event. This is not concrete. I mean, by by definition, when you cut something and you can't see all these particles and they make you cry, this is something that's super abstract. And it's not as abstract as what they need to be doing in 6-8, but it's not a concrete event. So we tag this as a grade level 3-5 because students do need to be looking at a representation of this. They're not developing their models. They're kind of looking at a representation of what's happening between the solid and the particles, and the DCI is that particles are too small to be seen. So this is a grade level 3-5. How do mushrooms create usable energy? So we have these these little organisms, and they are erupting out of this tree, and they're going num num nums on the tree and recycling energy and matter and lots of good things back into the environment. So we ask students to draw a model to show the flow of energy into and out of these mushrooms in their ecosystem, and then explain how your model shows. This is not a concrete event. This is something that's much more abstract than this. You could say that it's grade level 3-5, but because we're looking at energy is intangible, and it like changes form between all of these different, it's like going from being in this tree to then allowing these mushrooms to grow, and then like I'm gonna go eat them and it's gonna give me energy, and then it'll leave my body as heat in some ways. It's a real abstract thing. So in movement of energy through an ecosystem, this is an abstract thing. This is a grade level 6-8, not only in content, but also in level of rigor of the SEP. This is a phenomenon. Why is radioactive decay dangerous? So there was an incident in Brazil where some folks broke into an abandoned hospital and they pulled apart a machine and they saw stuff that glowed blue, like in this GIF right here. Not good, people. Please don't do this. So we ask students to draw a model to show how this radioactive decay occurs and then why it's dangerous to living things. And I'm doing these things with my hands because that's important in all of this. So again, colorful bar down there at the bottom. We know that this is not a concrete event. Radioactive decay is markedly abstract and difficult to observe. So grade levels 3-5, we're looking at representing events. In 6-8, we're looking at abstract phenomena. So this is a grade level 9-12. And the reason why is that they're showing relationships among variables between systems. So there is a system undergoing radioactive decay. So these molecules or these atoms are shooting off these high energy particles and changing. And then there's a separate system, which is the living system. So that cell, and really what we're looking at here is the DNA. And those high energy particles just slice right through that DNA, and it's not good. So I shouldn't be laughing. But the idea here is that we're able to show relationships between two different systems. And so at the 9-12 level, if students are just drawing a model of a singular system, they are hitting them. There is an element within 9-12 that allows you to look at variables within a system, but 9-12 should be showing levels between two systems. So if you're asking students in middle school to do that, calm down, just do one system. But at the high school level, that is what they need to be doing. Now we're gonna look at the details. So the elements in each grade level band. And so I'm gonna give you a grade level band, and you all are gonna use your annotation tool, do some analysis of what coverage we have of this standard. For our first example, it's onions. It's onions. So we have pictures A and B. I'm not going to read the whole prompt again. What I'm going to focus on, though, is what you need to do on the other side of the screen. So what I'd like you to do is to choose what elements, and the answer can be one or it could be many. But I want you to decide and use your annotation tool. Go ahead and give us a little stamp here. So does this cover element A? Are there limitations of models here? And you can use this little box over here on the side. So are students identifying a limitation of a model here? Are they looking at relationships among variables? Are they describing a scientific principle or design solution? Are they developing or using a model to describe and predict phenomena? Are they conveying a proposed object, tool, or process? And are they testing cause and effect? So I'd like you to take your stamper and go ahead and lay out on the right-hand side of the screen what elements you think are being covered in this question. Go ahead and keep on annotating if you'd like, but I'm going to go over my analysis of this. So because we have students looking at these models and they're really just using them to describe or predict phenomena, they aren't developing anything. So for B, it's collaboratively develop or revise a model. They do not need to revise models A and B. Here you go, kids, here are your models. For C, they're not developing a model using an analogy. There are models that are given to them. What they're really doing is D, which is using a model to describe or predict phenomena. So there's a phenomena here, which is that these onions make you cry. You can't see the things that do it, but they definitely do it. Students need to explain how this describes the phenomena. So really what we're hitting here is just D. So we're just using this to describe a phenomena. We're using a model to do that. All of these other elements ask students to look at cause and effect. You could maybe make an argument for the cause and effect in this, but what this question and this prompt is asking students to do is just look at this model and then explain what are these things, and it's just representing and using the model to represent. Okay, awesome work, everyone. New phenomena. There you go. Mount Pinatubo, it's this volcano, and it went kablooey, and all this particulate matter went out into the atmosphere. It literally changed the temperature in the northern hemisphere for like a year. It was a significant global event in terms of the climate. So we asked students here to draw a model in the space below to explain how the particles from this volcanic eruption will impact the climate. I already told you the answer. So, I want you to decide, are students evaluating limitations of a model? Are they looking at a variable or component of a system has changed? Are these uncertain and less predictable factors? Are they showing relationships among variables? Are they describing and predicting phenomena? Are they developing a model to describe unobservable mechanisms? What's going on here? And you can type stuff into the chat if you want. If you want to use the annotation tool, which y'all are obviously experts at, you can go ahead and do that. But let me know what you think this covers. So I'm going to go through my analysis of this just for time's sake, because we have more to go through and y'all aren't done yet with your annotations. Okay, so a variable or component of the system is definitely changing. So B is definitely correct. As far as uncertain and less predictable factors, you could probably make the argument that this is less predictable. I mean, unless you live in one of these places where things are erupting all the time and you see the particulate matter up in the air. I don't know. It's not really uncertain and less predictable. So I do appreciate that no one marked that one down. They are showing relationships among variables. So D is absolutely correct. They're definitely predicting and describing phenomena. That's like the most generic element in all of this. Like, is there a phenomena? Okay, great, you got this. And then unobservable mechanisms, I would argue that the answer is yes, there are definitely unobservable mechanisms going on here. And students can't see this particulate matter. It's just gonna get colder or warmer based on how this impacts the energy going into and out of the Earth system. So awesome job. So in middle school, in grade level 6-8, it's super generic. I mean, a lot of these bullet points overlap significantly. So showing relationships among variables, predicting or describing phenomena, unobservable mechanisms. Sometimes one of your questions can hit like 4 or 5 of these things. All right, we're done with this. Now we're gonna move on to the 9-12 level. And we're gonna talk about radioactivity again. So again, students are drawing a model to show how this radioactive decay occurs and why it's dangerous to living things. Again, doing things with my hands, important note. So you're going to go ahead, use your annotation tool. You don't need to wait for me to read them out, but I'll read them out for you anyways. So the first one is looking at the merits and limitations of 2 different models. The second one is designing a test to ascertain its reliability. C is illustrating or predicting the relationships between systems or between components of a system. D is develop multiple types of models. And then E is a complex model that allows for manipulation and testing. And then F is a mathematical or computational model to generate data, support explanations, or predict phenomena. There's a whole bunch of other stuff in there. Yeah, I mean, you guys know what's up. I've been pretty obvious about this for this, so good job. C is the only element. So in grade levels 9-12, it gets brutally specific with what they want students to do. So you're either looking at reliability, you're either looking at multiple models, or you're showing relationships between systems or elements of a system. If you don't have multiple models, then you can't possibly hit A or D. Those are explicitly stated, and they need to be looking at multiple models and sometimes moving between different models to talk about which one is better for certain cases. So awesome work, y'all. That's exactly right. Let's talk about scaffolding this up, because this is kind of the element of this I think is unclear. And as we've talked to teachers, and it doesn't matter what grade level you're in, if you're in 3-5, you're like, they come to me with no science knowledge. If you're in 6-8, you're like, they come to me with no science knowledge. And if you're a high school teacher, you're like, they come to me with no science knowledge. And the skills are even tougher, because these are things that, I mean, they're meant to develop over the course of 10 years as students get into high school. So if they've done none of this before, you need to scaffold up to it. So let's talk about this. We're gonna use the same phenomena, Mount Pinatubo, kablooey, and we're gonna look at how we can ask students to model what's going on in this phenomena. So for 3.5, we're going to look at draw a model to show where these smoke particles come from and where they go when a volcano erupts. So can you show me that particles come from one place and they go somewhere else? And so students just need to represent what's going on. So they're developing a model to show, to describe a process, and then they're also showing where they're predicting or describing phenomena. And so real simple, grades 3.5, use Mount Pinatubo, just draw me a picture. And if you give them these representation questions first, then you can start to show the models to students and say, like, yeah, absolutely. If you give students, like, this is what a model looks like to show particles doing a thing, going from one place to another, you got it. And then you can get to the more complex things at grade level 6.8. And here we're going to ask you to draw a model to show how particles from this volcanic eruption will change the climate where you live. What I love about this is students could probably make an argument for this making things warmer or colder based on how they think energy is going to interact with that. And so this is hitting a bunch of elements. 6.8, again, 6.8 is like the most generic with a bunch of the bullet points and the elements that we need to hit. So students are drawing a model. They're showing what happens if a variable is changed. These are unobservable mechanisms. It's less predictable. Like, I don't know, if you live in New York, you're probably not thinking like, have there been any volcanic eruptions and how will that impact my climate next year? No, there are broader things in play. So lots of elements in 6.8. This will help you scaffold up to 9.12, where it gets even more complex. Draw a model to show how Mount Pinatubo's eruption changes energy as it enters the Earth system. So coming from this other thing, like the sun, and it's going into the system, as it's stored in the system. So there's, the greenhouse effect and all these other factors that go into how energy is stored, and then as it exits the Earth system. So now we're looking at how things are going in and out of the Earth system. In 9.12, again, it is so specific. So this just hits one element of there, which is interactions between variables within or between systems. And that's it. If you allow students to use the same phenomena in 3 different formative assessments, to allow them to represent particle matter, allow them to show how that particle matter might impact energy in the system, maybe as it's stored in the system or as it enters the system, and then later on showing this really complex, then you're going to have a much better time with students doing the really complex stuff they need to do at high school. So this is really meant for you, like high school and middle school teachers that are looking to give students just some steps to get up to where they need to be, because it gets tough. And guess what? We do this. We spend so much time nerding out on this, and we write questions that scaffold up. So if you're a high school teacher, you can assign some 4th or 5th grade questions. If you're a middle school teacher, you can do the same things. And then we report out on all these elements because all the questions are tagged with this. So please find a time to chat with us. We'll drop the link to our calendar in the chat, and we'd love to help you. You can try the site out for a little while, pilot it or trial it, whatever you want to call that, with your students and teachers.
Awesome. So now that we have some understanding of how to use the progressions and the elements of an SEP to analyze questions for complexity and detail, we're now going to put it all together with one more phenomenon, because we just can't get enough of them around here, and a sample set of questions. So this last activity is a quick one, but it's an example of how you can apply these principles to your own assessments, and it continues to highlight how we think about and write and tag assessment items on InterOrbit. So here is our example phenomenon. So in this GIF, we see a terrifying mudslide in this little car just going along for the ride. Yikes. We can attest that everybody is safe and fine in this, but for science, we're going to use this for an assessment. So in the upcoming questions, again, I want you to think about the complexity of the SEP developing and using models that students are being asked to perform. So here's the prompt. In the space below, create a model that shows how water would start in the ocean and end up flowing down a hill. Explain those things. And then explain how your model shows the ways that gravity helps to cycle water between the atmosphere and the Earth's surface. So one more time, we're going to go through the grade bands and look for the level of complexity first. So you can use your stamp feature. I'll go ahead and read through them too, but we're going to first start in K2. So in this prompt, are students using and developing models to represent a concrete event? Are students building and revising simple models or using models to represent events and design solutions? Are students being asked to describe, test, predict more abstract phenomena? Or are students synthesizing, predicting, showing relationships between variables between systems and their components?
I love that the answers here are all across the board, and this just
Yeah.
goes to show how difficult it is to interpret these questions and to figure this out in less. And as somebody who writes these all day long, it's just difficult to even communicate the intent.
So let's go ahead and share our analysis of what the level of complexity this SEP questions are trying to assess.
Cool. So this should be grade levels 6, 8. And the reason is that we're looking at something pretty abstract, and the question about gravity is what brings it up to grade level 6, 8. You could probably say that it's grade levels 9, 12, I guess. But most of the complexity at 9, 12, it would be, like I think you'd have to bring energy into it and talk about gravity, or talk about how like each of the different spheres is interacting separately. But truly, this is intended for grade level 6, 8. So we're looking at the water cycle, and we're also looking at just representing how gravity helps to cycle the water between those systems. That's it. It's a singular system. We're not getting more complex. So 9, 12, I don't know, kind of shaky grounds, but this is intended for 6, 8. And grade levels 3, 5. So if we were just representing the water cycle, then absolutely. But throwing gravity in there kind of gives students a curveball. It's much more abstract. And so we would mark this question as grade level 6, 8.
Awesome. So now that we know the complexity and we know that it's grade band 6, 8, and it's now analyzed for level of detail and coverage that these questions are assessing. So again, students are creating a model to show how water would start in the ocean and end up flowing down a hill. They're going to explain that. But then they're also, question number 3 is explain how your model shows the ways that gravity helps to cycle the water between the atmosphere and the Earth's surface. So let's go through all of the elements of this specific grade band to see what's the level of detail. So you guys can start stamping, but I'll also read through them so you can think them as well. So are students in their model evaluating limitations of their model? Are they developing or modifying a model showing when a variable or component of a system is changed? Are they developing a model that have uncertain and less predictable factors? Are they developing, rising a model to show the relationships among variables? Are they predicting or describing phenomena in their models? Are they describing unobservable mechanisms in their models? Or are they generating data to test ideas in their models? So you guys are crushing it.
Can you all see our next slide? Because this is like fantastic analysis. Let's keep these annotations up, Erin, and we'll
fantastic.
We'll do our next one. So yeah, so this shows the relationships among variables. Absolutely. Students are definitely predicting or describing phenomena, and they're looking at unobservable mechanisms. You cannot see gravity. It is a thing that is happening to everything, but you can't really see it. It's an unobservable. We see the results of it, but not the actual thing. So awesome job, y'all. That is exactly right.
Beautiful. Well, for time's sake, we are 5 minutes out, so it is time to wrap up. Oh my gosh, how fast an hour can fly. So all of the things we talked about in 60 minutes are quite complex. So let's review them one more time just to cognitively wrap them up. So we accomplished our objective of being able to analyze questions, assessing the SEP, developing and using models for complexity and detail. We talked about how the K-12 progressions help you analyze that complexity level first, and then when you look at the elements underneath, that helps you understand the detail or the coverage that you are assessing students towards. And we also talked about why would you do this? So knowing the progressions, the complexity, and knowing the elements and the detail will help you scaffold students up to where you need them to be at your current grade level. That helps not only design your curricula, but your assessments feed into that. So if you're assessing students on those discrete elements, you know exactly where to spend your precious instructional time. So if you know they're doing well on one specific element of your current grade band, but see in a prior grade band they need more support, that's where you can intentionally focus your time in your instruction. So that's really what data-driven practice is being able to know where students are specifically in your current snapshot in your classroom, so then you can help them the best way you can. So speaking of that, we know all of this is really complicated, and that's why we made InterOrbit to help you all go further faster with not only providing amazing phenomena and assessment items, but having really discrete tagging and reports that help you know where to spend your time instructionally. So we'd love to offer you free pilots to check out our site so you get to fully explore these questions that we've been examining today. And then we also provide these sessions for schools to talk about this specific practice of assessing this SEP, developing and using models, but in your context in a little bit more collaborative type of format. So again, thank you guys so much for being active with us today, participating, contributing, asking amazing questions. That's what we're here to do. So once you've submitted your exit survey, you guys are good to go. Have a wonderful rest of your week. If there are any further questions that we can help you with, feel free to drop them in the chat. That's a great question, Justin. So you can still have current grade level content, so your current grade level DCIs, but ask students to model at a prior grade band element. So that's kind of where you can kind of like mix and match the 3 dimensions to scaffold students up to their current grade level understanding. So really deeply dive into those elements, like know your current, content, but then ask them to model maybe at a prior grade band and use those elements there. Beautiful. Thank you all.
All right. Bye, everyone.
Thank you
Have a
guys
beautiful
so
day.
much.
Thank you.
Bye.